Hello and welcome to this video which is 36th set of problems on complex numbers. There will be I think one or two more sets and then we will move on to theory of equations. So if you are new to the channel, then make sure that you subscribe to the channel and press the bell icon so that you can get notified about more such videos on complex numbers and upcoming topics on algebra. After algebra we will move on to trigonometry and calculus and so on. So without further ado, let's get started. As always, I will say that when I'm reading the problem, you should pause the video. And if you cannot solve the problem, only then look at the solution. So we have this problem 351, which says prove the equality sin n theta by cos to the power n theta is equal to nc1 tan theta minus nc3 tan cube theta plus nc5 tan 5 theta and so on, where a is equal to minus 1 to the power n minus 2 by 2 into n nc n minus 1 tan to the power n minus 1 theta. If n is odd, a is equal to minus 1 to the power n by 2 dot tan to the power n theta if n is odd. This should be even. Okay. So we have cos theta plus I sin theta whole to the power n is equal to cos power n theta plus I into nc1 cos to the power n minus 1 sin theta plus I square nc2 cos to the power n minus 2 theta sin square theta and so on. So we separate the imaginary parts. We have sin n theta is equal to nc1 cos to the power n minus 1 theta sin theta minus nc3 cos n minus 3 theta sin cube theta. So you take into account the parity of n and divide both members of these equalities, that is left hand side and right hand side, by cos to the power n theta. We get the required formula. Question 352 says that 2 to the power 2m cos to the power 2mx is equal to sigma k is equal to 0 to m minus 1 2m choose k cos 2m minus kx plus 2m choose m. So we know that cos theta is equal to cos theta plus I sin theta plus cos theta minus I sin theta by 2. Now we let cos theta plus I sin theta is equal to z, then cos theta minus I sin theta is equal to z inverse. So cos to the power 2m theta is equal to z plus z inverse by 2 whole to the power 2m. Now this can be written as 1 by 2 to the power 2m sigma k is equal to 0 to 2m 2m ck z to the power 2m minus k dot z to the power minus k. That is 2 to the power 2m cos 2m theta is equal to sigma k is equal to 0 to m minus 1 2m ck z to the power 2 m minus k plus 2m cm plus k is equal to m plus 1 to the power 2m 2m ck z to the power 2m minus k. Now we put m minus k is equal to minus m minus k prime. We rewrite the sum as sigma k dash is equal to m minus 1 to 0 2m c 2m minus k prime z to the power minus 2m minus k prime is equal to sigma k is equal to 0 to m minus 1 2m ck z to the power minus 2m minus k. So this identity which we have here, it becomes 2 to the power 2m cos to the power 2m theta is equal to sigma k is equal to 0 to m minus 1 2m ck z to the power 2m minus k plus z to the power minus 2m minus k plus 2m cm. But from this formula over here, this formula, we have z to the power 2m minus k plus z to the power minus 2m minus k is equal to 2 cos 2m minus k, which means 2 to the power 2m cos to the power 2m theta is equal to sigma k is equal to 0 to the power 2m minus k 2m choose k cos 2m minus kx plus 2m choose cm. So now question 353 says that prove the following equality 2 to the power 2m sin to the power 2mx is equal to sigma k is equal to 0 to m minus k minus 1 to the power m plus k 2m choose k cos 2m minus kx plus 2m choose m. Now we put theta is equal to pi by 2 minus theta in the previous problem and we will have the required formula. Question 354 says that prove the following equality 2 to the power 2m cos 2m plus cos to the power 2m plus 1x is equal to sigma k is equal to 0 to m 2m plus 1 choose k cos 2m minus 2k plus 1x. So like previous problem, you can solve this. Prove the following equality: 2 to the power 2m sine to the power 2m plus 1 x is equal to sigma k is equal to 0 to m minus 1 to the power m plus 1 to 2m plus 1 choose k cos 2m minus 2k plus 1. Once you solve problem 354, you substitute theta is equal to pi by 2 minus theta and then it will be proved. Question 356 says that let un is equal to cos alpha plus r cos alpha plus theta r square cos alpha plus 2 thetas and so on up to r to the power n cos alpha plus n theta. Vn is equal to sin alpha plus r sin alpha plus theta plus r square sin alpha plus 2 theta up to r to the power n sin alpha plus n theta. Then show that un is equal to cos alpha minus r cos alpha minus theta minus r to the power n plus 1 cos alpha plus n plus 1 theta plus r to the power n plus 2 cos alpha plus n theta divided by 1 minus 2r cos theta plus r square. And Vn is equal to sin alpha minus r sin alpha minus theta minus r to the power n plus 1 sin alpha plus n plus 1 theta plus r to the power n plus 2 alpha, sin alpha plus n theta divided by 1 minus 2r cos theta plus r square. So we write the expression un plus ivn is equal to cos alpha plus r I sin alpha plus r cos alpha plus theta I sin alpha plus theta up to r to the power n cos alpha plus n theta plus I sin alpha plus n theta. Now we take out cos alpha plus I sin alpha, so we will be left with 1 plus cos theta plus I sin theta plus up to r to the power n cos n theta plus I sin n theta. Now we put z is equal to cos theta plus I sin theta, then un plus ivn becomes cos alpha plus I sin alpha into 1 plus rz plus r square z square plus and so on up to r to the power n z to the power n. That is e to the power I alpha into rz whole to the power n plus 1 minus 1 by rz minus 1. Now we separating the real and imaginary parts. What we have is rz whole to the power n plus 1 minus 1 by rz minus 1 is equal to there should be a square here. No, we are not squaring. We just multiply and divide by rz bar minus 1. We just multiply it by and divide by rz bar minus 1. So it becomes r to the power n plus 2 cos theta plus I sin n theta minus r cos theta minus I sin theta divided by 1 minus 2r cos theta plus r square plus minus r to the power n plus 1 cos n plus 1 theta plus I sin n plus 1 theta plus 1 divided by 1 minus 2r cos theta plus r square. Now multiplying this with cos alpha plus I sin alpha, we have un plus vn is equal to given expressions. Now we put alpha is equal to 0, and so from this we have the required condition. We put alpha is equal to 0, we obtain 1 plus cos theta up to cos n theta is equal to sin n plus 1 by 2 theta cos n theta by 2 divided by sin theta by 2, and similarly for the sum of sine terms. Question 357 says that simplify the following sums: s is equal to 1 plus n cos theta plus n into n minus 1 by 1 into 2 cos theta and so on up is equal to sigma k is equal to 0 to n nck cos k theta, where nc 0 is equal to 1. S prime is equal to 1 plus n sin theta plus n into n minus 1 by 1 into 2 sin 2 theta plus so on is equal to sigma k is equal to 0 to power n nck sin k theta, where nc 0 is also 1 again. So what we do is we take the sums as s plus I s prime is equal to sigma k is equal to 0 to n nck cos k theta plus I sin k theta, which is equal to sigma k is equal to 0 to power n cos theta plus I sin theta whole to the power k, which is equal to 1 plus cos theta plus I sin theta whole to the power n, which is equal to 2 cos square theta by 2 plus 2 I sin theta by 2 cos theta by 2 to the power n, which is equal to eventually 2 to the power n cos to the power n theta by 2 into cos n theta by 2 plus I sin n theta by 2. Now we equate the real and imaginary parts and we get the values for s and s prime. Question 358 says that if alpha is equal to pi by 2n and p less than 2n, where p is a positive integer, then prove that sin to the power 2p alpha plus sin to the power 2p2 alpha and so on up to sin to the power 2p n alpha is equal to half plus n into 1.3.5 and so on up to 2p minus 1 divided by 2.4 up to 2p. So we put s is equal to so much, which is equal to sigma L is equal to 1 to the power n sine to the power 2p L alpha. But earlier we have proven that sine to the power 2p L alpha is equal to 1 by 2 to the power 2p minus 1 minus 1 to the power p sigma k is equal to 0 to p minus 1 2p ck cos 2pk minus L alpha plus 1 by 2 to the power 2p 2p cp. Therefore, our s becomes minus 1 to the power p by 2 to the power 2p minus 1 sigma k is equal to 0 to p minus 1 into not into minus 1 to the power k 2p ck sigma L is equal to 1. There should be a plus sign here. L is equal to 1 to n, or not is plus, is equal to sign should be there. There is something missing here. I'll fix this in the next slide. Sigma L is equal to 1 to n cos 2 p minus k into L alpha plus 1 by 2 to the power 2p 2p cp. Now we put 2p minus k alpha is equal to theta. So sigma L is equal to 1 to the power n cos 2 p k minus alpha becomes cos theta plus cos 2 theta and so on up to cos n theta, which we have found to be sin n theta by 2 dot cos n plus 1 theta by 2 by sin theta by 2. Now we denote this by sigma k. We can prove that sigma k is 0 if k is of the same parity as p, that is k is equivalent to p mod 2, and sigma k is equal to minus 1 if k and p are of different parity, that is k is equal to p plus 1 mod 2. So we get x is equal to minus 1 to the power p plus 1 to the power 2p minus 1 sigma k is equal to 0 or k equivalent to p plus 1 mod 2 p to up to p minus 1 minus 1 to the power k 2p ck plus n by 2 to the power 2p 2p cp. Hence x is equal to 1 by 2 to the power 2p minus 1 sigma k is equal to 0 k equivalent to p plus 1 mod 2 p minus 1 2p ck plus n by 2 to the power 2p 2p cp. But we can prove that sigma k is equal to 0 k equivalent p plus 1 mod 2 p up to p minus 1 2p ck is equal to 2 to the power 2p minus 1, and thus we have proven the desired result. Question 359 says that prove that x plus y to the power n minus x to the power n minus y to the power n is divisible by xy x plus y into x plus y into x square plus xy plus y square if n is odd number and not divisible by 3. So considering the given polynomial as y in y, we see that y at y is equal to 0 the polynomial vanishes. Therefore our polynomial is divisible by p. Since it is symmetrical with both with respect to x and y, this must also be true for x, that is the polynomial being divisible by x. Hence the polynomial is divisible by xy. Putting y is equal to minus x, we have x minus x whole to the power n minus x to the power n minus minus x to the power n. Consequently, the polynomial is divisible by x plus y. So you see that this becomes 0. So polynomial is divisible by x plus y because it is symmetrical with respect to x and y. Now it remains to prove that the polynomial is divisible by x square plus xy plus y square. I expand this into real factor. We get x square plus xy plus y square is equal to y minus x omega into y minus x omega square, where omega is the cube root of unity, which leads to the fact that 1 plus omega square is equal to 0. Since n is equal to 3m plus 1 or 3m plus 2, we substitute x is equal to y is equal to x omega and y is equal to x omega square and find that it vanishes for both. Consequently, we have proven the divisibility condition. Question 360 says that prove that x plus y to the power n minus x to the power n minus y to the power n is divisible by xy into x plus y into x square plus xy plus y square whole to the power 6 if n when divisible by 6 has a remainder of 1. So we let the quantities minus x minus y and x plus y be the roots of the cubic equation x cube minus rx square minus px minus q. Then r is equal to minus x minus y plus y is equal to 0 minus p is equal to xy minus x into x plus y minus y into x plus y, q is equal to xy into x plus y. This is from Vieta's relations. So this reduces our equation to x cube minus px plus cube is equal to 0. Now we put Sn is equal to x plus y to the power n minus x to the power n minus y to the power n. We find that between successive values of Sn there exists a relationship Sn plus 3 is equal to P Sn plus 1 plus Q Sn. We use the mathematical induction to prove that Sn is divisible by P square with the knowledge that S1 is equal to 0. Now we let Sn be divisible by P square for mathematical induction, and then we let Sn plus 6 be also divisible by P square. So Sn plus 6 is equal to P Sn plus 4 plus Q Sn plus 3. So Sn plus 4 is equal to P Sn plus 2 plus Q Sn plus 1. Therefore, Sn plus 6 is equal to P into P Sn plus 2 plus Q Sn plus 1 plus Q P in Q into P Sn plus 1 plus Q Sn. That is P square Sn plus 2 plus 2PQ Sn plus 1 plus Q square Sn. Since by supposition Sn is divisible by P square, it suffices to prove that Sn plus 1 is divisible by P. Thus, we only have to prove that given expression is divisible by x square plus xy plus y square if n equivalent to 2 mod 6, which can be proved by proceeding like previous problem. So with this, we come to the end of 36th set of problems on complex numbers. I hope that you have found this video useful. So please like the video, share it, and make use of the comment box so that we can interact. And if you have any doubts, I can solve it. I ask for this so that the video reaches and it helps to benefit other people like you. So thanks a lot for watching. Have a nice day.